Hello, this is Fred LaPolla from the Health Sciences Library, and welcome back to the last section of the beginning part of this class on sequencing informatics. And so this is the last part being the portion that's been the introduction to R. So thank you to those who have joined with us week after week. So as in past weeks, I'd like to encourage you, as any questions arise, to post them to the group chat if it's about something that we're discussing immediately. If it's a question generally about R or about another topic relating to the general topic, I would encourage you to use either Slack or Stack Overflow. So there's a class Stack Overflow that's been set up. But again, the chat's probably the best way to go, and we have a number of TAs with us today who can help answer those questions. So last time on Tuesday, we finished up discussing data visualization. We talked about ggplot2, a package that is widely used in R for data visualization, and how it encodes the different elements of a chart or a visual using layers. So you would encode the aesthetic layer, so that AES command saying what our X value, our Y value, what colors might be coding to. And then we add layers for different shapes, or the geom command, the geom, for example, underscore point or underscore bar. We added layers for themes to update the backgrounds of the chart. We added layers to set the scales. So if we didn't like the default scaling, we might, for example, change the increments that a scatter plot is presenting in. And we also added layers for things like error bars that we might want to add on top of our bar plots, allowing us to create a figure that we could produce and publish. Then from there, we moved on. We talked a bit about various hypothesis tests in R. And depending on where we are, I may return to that topic. But I think actually I'm going to sort of change gears a little bit and talk about data cleaning, which I think in terms of regular use of R for analysis will be an area that you spend a lot of time. It's, in terms of difficulty, not probably as complex as maybe certain things might be, but in terms of having to do things over and over and really explore your data, make sure it's in the correct format for you to run your actual analyses. Unfortunately, or just the nature of it is that it is a major part of where you will all be spending time in R, at least in my experience and the experience of others, before you can get things in the shape that you can actually analyze them. So I'm just going to keep using our same NYC Haynes data, which does have a fair amount of NAs we saw that we can work with. And so basically by data cleaning, what I really mean is that the way that the data that's getting read in, so when we load a data frame, a data table, often it will not appear as we ultimately want it to. Oops. So one of the first topics that we might want to think about is, how does R treat blank values? So I made a very, very tiny, nonsensical spreadsheet full of blank values just to make it very clear to us. So 5 columns, one of which is not labeled. Let's see, do I even have it open? I don't have it open as a spreadsheet, and I'm not going to look for it this late in the game, but basically an A, B, C, D, and there is an E, which is unlabeled with some text values in it. And if we were to go ahead and read it in, we would find that NAs appear for missing values. So yeah, if I read it in here, although in the original spreadsheet, the original comma-separated value file, these were merely blank items. When we read it into R, it's going to be treated as an NA. And so there's a few ways we could deal with it, but as you may recall from the first couple of workshops we did on introductory use of R, it is the case that certain functions are not going to be able to work with NA. And in fact, this is actually a good feature of R. So we would not want R, as is the case with, say, a tool like Excel, to assume that NA actually means 0 or a blank means 0. So if you were to have a column with some numbers and some missing, and you were to sum the whole column in a tool like Excel, it would give you a sum, and it would just sort of view those blanks as zeros. But that might not actually be accurate. They might not be zero. So if we were doing something like finding a mean of a group, if we treat it like zero, when it's not a zero, when it's maybe just an error or there's some reason we couldn't collect at that data point, that's going to kind of skew our results off. Maybe skew is the wrong word, but that's going to move our mean in a way that is not actually representative of the physical phenomenon that we're measuring. So it can be really good for us to think about that this is a nice thing, but it does mean that in R, we do have to be kind of conscious about what those blanks will mean. So yeah, there's a few ways we can deal with that. So one command that can be really nice to get familiar with is the is.na command. And basically is.na will iterate over a vector of some sort and look for any NAs. So if we were to run it and return a true or false, so it provides a logical statement. So if we were to just do it over that first column, which as we saw was had one NA and 4 numbers, we can see that we get 4 falses and a true. So we can actually then use that using those logical operators that we talked about a few weeks back now, and indexing, which I think we talked about way back on the first day, to provide R with a command saying, feed into the index of this data frame, not, so the exclamation point, not is.na, and then the NAs of this column. So it's basically saying, start here, start with this vector, go over, find any NAs. Then if it's an NA, if it's true, say not that one, and then use that number, use that index to specify a row in this data frame. So when we get this no NA and A, it will be a table without any NAs in that first column. So it may be getting into the realm of tongue twister, but this can be nice because this can be a way that we can remove those blank values from a column or vector of our data that we don't want to have those NAs existing. So we can run our analysis and it won't be thrown off. If we had treated it as a 0, then we would have been artificially lowering our mean value and lowering whatever other types of analyses that we might do. So we could also do something equivalent to look at any fields, any rows where there are these blanks to then see, maybe there's some issue, maybe we can investigate why we were getting NAs for a given column and find the problems and be able to address them. So in this example, we used one option for dealing with those blanks, which was to just get rid of them from the first column. In some cases, this is going to be an optimal option. In other cases, you might want to impute a value depending on what it is you're doing. So you might add a median or mean value of the rest of the column there. But for right now, I'm just going to say for this, we just removed those NAs and did not include them. So there's also related arguments such as is NaN for not a number for situations where you have a non, I think that'd be something like if you divided infinity by negative infinity, I think. But I forget exactly the criteria for not a number at the moment, although I just looked it up previous to now. Also things like is infinite. So if you have these kind of mathematic figures that might be throwing things off, I'll say that those might be less common cases, but just good to be aware. So one option we do have for getting rid of NAs is just this na.omit. So perhaps I want to get rid of every row of my NYC table that has, or my NYC data frame that has a NA in it. So I could try something like na.omit. So if I just run this, we can see I've got 1,112 rows. And if I was to do that, I'll do this down here. Maybe I'll just make a few lines just to make it clear. NYC and read it over itself. Did it not remove any? Perhaps did I already? Oh, I did it up here. Excuse me. Let's just actually redo that then. So if we do those, we have could do something like length, but we have got 1527. So it removes a fair amount if we are to do the na.omit. So it can be a pretty intensive way of removing things. So it might not always be super appropriate depending on what it is that we're trying to do with our analyses. But in some cases, it may be the best option that we just realize that these rows are not going to be useful to us, so we want to remove any row. That said, we could also use na.omit over a given vector of values so as to not be losing as many of our rows of data. So we might not want to run it over all of NYC, but let's say we are interested in cholesterol or any of these other variables, we might run the na.omit on that given column so as to remove the rows that have NAs from that. And we may still have blanks in different rows, but for that analysis, it might not matter at the moment. That said, removing the NAs is one option of many. In other cases, we might want to replace or recode values. So you may have noted, looking back a few pages, in the beginning of column C, we have 999. That's way outside of the range of the rest of these values. And so sometimes, frequently, certainly in the kind of the more clinical realm for surveys, whoops, I guess I'm now drawing on my screen. Should turn off the annotation. Let's see. Nope. In any event, maybe that's not visible, but we've got some annotations here. So ignore these red lines. And so it may be the case that we, what's the word? Have something like a 999. So that's an example that perhaps may be more common in things like surveys and in clinical areas where if we have questions such as where we're perhaps surveying somebody and we want to have an option for refuse to answer or don't know, we don't want to necessarily just leave that blank, as that might imply, you know, that's pretty obscure what that means. So we might want to assign it with some value like don't know or can't answer. So instead of it being a blank where it's unclear what it means, we have this figure that's well outside the realm of possible values, but it signifies to us, the data analyst, oh, okay, that's either a missing or refused to answer or so on. So it may be the case, that was a long way of getting to, it may be the case that we want to replace this 999 with something. Perhaps we actually do want to replace it with NA and then code to remove the NAs in that way. So we could run a command called replace, and similar to other commands, we have first, it will feed in a data object. So here we're just feeding in this third column of our tiny sample data frame. And we're saying if that is equal to 999, 9,999, recode it with NA. So for these in this column, when they are this value, set to NA. So we can do that. And previously we had a bunch of nines, and now we have the NA. So that's one way that we could deal with replacing certain values within our data frame. We may also choose to recode values. So using the tidyverse again. So a lot of this is just sort of the syntax spelling out that the tidyverse is in place. But so we could, there's actually many ways we might want to do this, but here is another way. And in general, I think that's going to be the rule for working with R's. There's going to be multiple ways. But that said, these tidyverse options give us some nice ability. So perhaps when we initially read in our data, I had read it in so as to call the ones male and twos female previously. But let's say we didn't know what the values were going to code to right when we read in our data and we wanted to explore it a little. we might then go back and recode things once we realize, oh, it's listing these in the incorrect way. So here we'll just give it 1 equals male, 2 equals female. For whatever reason, for these numbers, it will require this. It's not quite the single quote mark, it's more the accent mark that's next to the 1, at least on my keyboard, which signifies that it's getting some factor number, and we can just recode things that way. So very similar to the replace, where we're providing it with the data object, and then we're saying this set to this, and so on. So it may be a good option for working with your recoding and renaming those values that may either be missing or may in some way be problematic. So we talked about previously, though I do kind of want to bring it up again, that sometimes the data, the classes of the columns or the parts of our data frame will be incorrect. So I do want to just sort of bring up a reminder in the context of data cleaning that this will often also be a step that can be useful for changing how our data is displaying. So one thing that may strike you when we first read in our NYC, if we leave it as a default, that first column in NYC, I'll do head NYC 1. We can see it is a series of basically key identifiers for the data in our project. So we've got just numbers with a letter. Not sure, I tried to look into if that letter is significant or meaningful in some way. I could not quickly or readily figure out if that was the case. So it may have meaning to the administrators of the study. But something else that pops out at me is it gives me levels, which when it has levels, that's a giveaway that it's classifying our data as a factor, because the levels will basically be referring to the groups in our factor. So a factor can be thought of as a group type variable. So we have things you can see up here, like the age group, levels 1, 2, and 3, young, middle, aged. So when it's listing these levels, it's not really treating our data as a bunch of strings, character strings, as we might tend to think of a subject ID. Instead, it's labeling them more as levels. And we can even see that there's 1527, so it's every row is its own level, which would probably in most cases not be the most useful way of thinking of a factor, since every group is unto its own. So one option we have is actually, if we went in when we read things in, we might choose to change, set strings as factors to false. So if there were strings that were, for example, young, middle, aged, we might not want to turn this off. But in cases where we know we have lots of strings that are characters, so another example would be if we had a list of either genes or the identifiers that are provided by the processor for gene expression that aren't really meaningful in the same way as names of genes. They aren't maybe meaningful to the researcher in the same way. We might want to set these as false, since there's going to be 1 per row, and it's not really going to be super meaningful to treat that as a factor variable. So we could do that, and it will reclassify things as a character value, or it won't change it from character to a factor. Conversely, if it is reading things in just as numbers, we may choose to use factor, apply it to the variable that we want to be a factor, and just give it these labels as we're going through. So there's definitely a few different ways, again, that we could work with getting our data clean and in a setup that we can analyze more easily. So one option, again, from dplyr, they make up that the dplyr package contains a lot of functions that will be useful with regards to data cleaning and getting our data in the state where we can then organize it and analyze it, rather, is called mutate. So in the class where we talked about functions and for loops and if and else statements, we talked about how you could create a new variable using if-else statements, but you may also choose to create variables using mutate. Basically, you can add a variable saying mutate, and here we're saying cholesterol total over HDL. So it leaves those two alone, but adds this new variable that is, in this case, a cholesterol ratio, but in your own data analysis might be something more specific to your own research. So we talked about dealing with NAs. At times as well, we may have cases where we have extraneous information in our table that is not really going to be relevant to our analysis. So there's a few ways we could deal with some of these things. So sometimes you'll have a CSV file where the first row or two, maybe the first row is not meaningful. It's just sort of like the names of the people who created it. Not to say that their names aren't meaningful, but just that there's not going to be part of our analysis. So you might read in functions with a skip. So you can do, there's an option to skip a few lines, and you can set the amount of lines as you're reading in the CSV. So similar to how we set the character strings as factors to false, you could also set, when you read in your CSV, to skip a few lines if you do have data that is, information about the data, not actually part of the data frame that you would normally analyze. You may also have cases where perhaps in the last column to the right, somebody has added their own annotations or notes, or written in information that was perhaps useful to them, hopefully useful to you, but might not be useful in the sense of something you want to read in. So you may have noted in the 5th column of this small, we had a missing note. Maybe somebody has annotated it in some way, but we want to get rid of that for the reason that, let's say we were going to make a heat map, any text that's in our matrix area is going to introduce problems in terms of creating it as a data frame rather than a matrix, or it's going to create it as a text-based matrix rather than a data frame. So all the values are going to be encoding as text. So one nice option, again, in the same realm of indexing, is we can apply this minus sign. So if we say -5 here after the comma, that will just delete out that 5th column that only had text in it. So it can be a useful thing to think about in terms of just getting rid of wholesale columns that were maybe taking up space or were being used for things like annotating data in a way that's not going to be super helpful for our analysis. You may also at times need to rename. So I'll say that the column names in the NYC Haynes database, for the most part, seem like they might be fine. It might be, more useful to spell out the SI a bit more. But in general, they may or may not meet your needs. But there will be definitely cases where the variables that have been assigned might be a little bit too cryptic, and you might want them to be something a little bit more understandable. And you can do that using rename. So we could go in and give this a new name here. And to me, somewhat confusingly, is the name on the left is going to be the new one. The name on the right is going to be the existing variable name. So I always find that a little bit counterintuitive, but perhaps you will find that intuitive and fine. So we could go in and give the variables a different name. And then if I just wanted to set it back, we can go down and provide that down here, just basically reversing the process. So again, another feature for renaming things, perhaps as you're using a tool like mutate or using if and else statements, you want to provide a new name to your new variables. So also, often when we are doing data cleaning, we'll really be combining a lot of the things we're talking about. So it may be the case that the data that we're reading in, so for example, the cholesterol data, is simply being provided in a continuous variable, so some number of cholesterol levels, total cholesterol levels. But we might, for our analysis purposes, want to dichotomize this in some way. So that can be a great time to think about combining some of the things we've talked about so far. So the first thing you might do is set up different groups for your analysis. So some grouping that would be meaningful to you. So in this case, I've just sort of divided things into high borderline, and normal. And so we're saying if it's in the highest group, to set things as high, the middle group borderline, and the low group normal. And you can see there's actually a nested if-else statement. So it's saying the first level if statement, the way this command works is if not this, then do this. Or no, if this, then do this. So it's if the cholesterol is over 239, assign it the value high. If not, and now we're nesting another if-else statement. So if not over 239, run it again, basically, for over 200. And if it's over 200, borderline, if not, normal. Something to note about doing this is that the order is really going to matter, because if we were to, say, reverse this, and we had started with if under 200, it may be, well, if under 200, it should also be fine. But basically, if the order isn't going to allow, if it's going to cause things to recode within things, within values in a way that's not sort of being able to be read across as it sort of iterates across, you may run into cases where you've already renamed your values from the numeric value to, say, a word like normal, and it may become somewhat confusing to work with, or it may not be able to process in the way that you expect it to. So that was sort of a garbled way of saying, as you're trying out data cleaning in ways that maybe are renaming values to sort of dichotomize them, it is just important to bear in mind that you don't want to accidentally rename variables over it. So yeah, in this case, this actually is non-destructive, and I'm reading this into the 24th column, which, as you may note, so currently, I apologize, I'm not sure if I can get rid of these red lines. Let's just try one thing. Erase. Yes. Okay. Those will be there for posterity. And yeah, so if you note, our NYC currently has 23 variables. And when we go in and we can assign, if we just assign something to NYC 24, let's just say for the sake of argument, just all NAs. Well, I'm not sure if that'll work. Yeah, now we have got a 24th variable, and if I say head NYC, not that we would, ever want to have this nothing 24th column, but we can just assign the 24th column as a placeholder for the previous one. So nothing has changed in my existing data, but it will sort of go in and find that there. So then after we've created these three groups for our dichotomy, we might then want to put that into a factor. So again, combining these different techniques to be able to then run some analysis. We might use these to see, are there differences? Do they correspond? Do they correlate to different values in some other variable of interest? At times, it may be necessary to use what are called regular expressions. My understanding of these are terms that are kind of more universally used in computer science and in other coding languages, which is why they're called regular expressions, though I could be mistaken about that, but that is my understanding. And so one that might be useful in the context of data cleaning is called grep, which I once knew what it stood for, but basically it's saying find some character string or some pattern basically from within whatever vector that you're pointing it towards. So perhaps it's the case that your subject IDs are maybe mashed together in some way, and it provides some information about, in the example that we talked about with heat maps, if it's the knockout versus wild type mice, if it's our NYC data, maybe it's that A or B, which unfortunately, again, could not figure out what that was referring to. But yeah, so it may be that there's some letter that has meaning to us, the person analyzing, that we want to be able to extract that in some way. So a real life example would be years ago, I worked on a study where the subject ID included information, included lettering that was meaningful to the members of the study, though would not have been meaningful to people who were not part of the study, that may have encoded, for example, which study site they came from, because it was a multi-site study, as well as I think perhaps if they were a parent or a caregiver. So perhaps it would be the case where we'd want to pull out only a subset that was being identified by, that's interesting, by what do you call it? I'm gonna just keep playing this game of cat and mouse, by the lettering that may appear. So in our, going back to our current example, perhaps we want to find only those subject IDs or those key numbers that have the A within it. So we could use that grep function to sort of work as a search of free text or of character patterns. So in this case, I'm just saying grep the letter A. And just in case it's not totally clear what I'm talking about, if I just do head NYC key, we can see the top view, it's A, B. They don't seem to, it's not like this one's 134040A, 134040B, but in any event, let's say we only wanted the A's and that was meaningful to us. So we could do this and we can say, assign this to a value called A's. And it says that there were 1,050 A's. And then we could use that again to view that subset as a subset. At other times, perhaps it would be useful to use a tool for string splitting. So there's a command called str split, string split. And so the best example that I could think of and that I saw was, let's say we have things like a zip code combined together. Another case might be, let's say we've done some sort of readout, and for whatever reason, the tool that's doing our reading, instead of separating things with commas or with spaces, maybe they've only added hyphens, and when we read it in, we didn't realize that, and now we've got this data with hyphens for when a new column should begin. Or for that matter, it could just be a things like given length. So let's just say for something that might be more universally familiar, we have all these zip codes. I made up these 4-digit after codes, so I'm not sure those are real locations. But if we wanted to split them apart, we could do string split, str split, and then I'm running this command called unlist. Basically, the default list data structure is just a little bit too complex for the string split to work over. And then we're saying split this at the hyphen. So again, those who maybe have worked with Excel for dividing data into columns, that if you have too many data points in one column and you realize, oh, every time there's a period or every time there's a hyphen, that should be a new column. This basically functions in the same way. And similarly, there's related commands for string trim, and you can actually set as an argument left or right. So if there's a bunch of blanks that have been sort of read in to the left or to the right of a text field, you can use those to kind of get rid of those and hopefully save some headaches in terms of how you are interacting with your data, so that hopefully it won't make any issues for you in working with your data. There's also the ability, so R can read in dates and times. So it may be the case that the date and time are important to your data, and so you've recorded that in some way. Perhaps it just read in as a text string, but you want that to be understood by R as a meaningful date or time that can be of use for your analysis. And so you can sort of say, like, how long after, for example, a given time did something happen, as opposed to viewing it as just a string. So a nice package to be aware of with regards to this is called lubridate. I think this again is part of that same tidyverse, that same set of Hadley Wickham created packages. But in any event, a common tool for working with dates you might work with. And so one of the commands that I've got here is, let's say we want to parse this from text values of dates to numerical dates. We could use the month, day, year dates. And so it's saying 4/23, April 23rd. I guess I did the same one, but, and it can then read that out into a format that's going to be nice to work with. I'll definitely say from experimenting with this, it's not foolproof. It can't understand, for example, typos. And if the orders are not all equivalent, in my experience, it's run into issues. So that might be a time where you have to explore through your data and do some of the things like we talked about earlier with replace, perhaps using indexing to overwrite given values with new values to get it in the format that you need it to. But if you are working with date and time data, this is a good thing to be aware that you can recode your values from just text string to a date formatted numerical value that then you could work with to sort of say how long did something take, essentially. So I think because we have a fair amount of time, I will jump back to discussing some of the hypothesis test options. But just to kind of review things from this, just be aware that you really should allot some time for data cleaning. It will definitely be a part of your data analysis process, especially as you first start out with reading data into R, and perhaps it may not always be formatted in quite the way that you want it to, and you have to kind of get used to it. Also getting familiar with what those different data classes and data structures mean with regards to your analysis. And definitely at first it will seem kind of exclusively academic, but as you kind of go on, you'll come to see why the data is encoded in different ways and how you can recode it. So again, using commands like factor or as matrix to move things to a factor, or matrix coerce them into those formats. Can be good to be aware of that there are options. And somewhat inconveniently, different packages really will sort of insist on different data types. So I think ggplot actually does insist on a data frame. So if you have a matrix, but you wanted to make a ggplot bar chart, say, with error bars, you would just need to run as.data.frame, and it would coerce it over from a matrix to a data frame. In general, that direction might be less likely to introduce problems for you because that data frame, if you remember, can have different types of data, whereas that matrix is going to be all numbers or all text or all factors. But good just to be aware that you can change those to get them in the format that you're going to need for your data analysis. So some tips before we sort of move back, I guess, just to some last thoughts on hypothesis testing, which, I mean, a lot of the analysis information will be discussed in the coming weeks with regards to RNA-seq and gene expression and working with the kind of the high volumes of data that you'll be working with. But I would definitely say for learning to use R and kind of getting past that point of lack of comfort, which hopefully we've helped somewhat to demystify working with a tool like R. But I would say just try using it in place of a time where you might normally use a spreadsheet or some other statistical tool. So if you've usually used SPSS or used Excel sheets, even for things that are kind of mundane, like just, you have a spreadsheet of times that people are spending in the lab and you just want to know what percentage were people doing different things. It can be good to just sort of force yourself to do the more time-consuming option of R to do that kind of analysis, and maybe it doesn't rise to the level of analysis, but understanding, kind of describing your data, whatever that may be. And I will definitely say from personal experience that it definitely does take more time at first, but over time, I think you will be able to get to a point where that discomfort goes away and the ability to do all of the different steps of analysis. So from cleaning your data, reshaping it into a way that you're going to be able to work with it, running some analysis and creating some sort of presentable report and figure, being able to do that all in one location, as well as being able to sort of just write out instructions to produce a kind of beginning to finish analysis can really save a lot of time and become much quicker than would be the case working with a point and click tool, especially a point and click tool like an Excel, where you can't really program it to kind of just churn through the results in the same way. I mean, I think you can if you really want to learn the macros, but from a really a power standpoint, R is going to get you a lot further for your learning, your learning effort. The other thing is you will definitely see lots of errors, not just as a beginner, just as you work with R and RStudio. Most of the time it's going to be a typo, but other times it's going to be you're trying to do something that's technically impossible, or there's some other problem relating to the structure of the data that you would not have been aware of before. And so definitely Googling your errors, really taking that specific error message and searching it, looking in Stack Overflow, saying, I was trying to make a heat map and I got, such and such error. And probably it's going to be the case that somebody has encountered, if not the exact same problem, something very, very similar. And so it can be good just to be aware that you have these resources like Stack Overflow to be able to look for solutions to those problems and kind of troubleshoot your data issues. And while it will feel slow and like every 5 minutes you're doing that at first, over time, I feel that it can be really worth the effort to get that, be able to do that analysis on your own and find those solutions. Also, when you're trying to do something, especially a common type issue that you may be encountering, there are great resources online. R Bloggers is one. There's another one called Quick R that I really like. I think it's maintained by DataCamp, but that hasn't always been the case. So I'm not really sure what the formal relationship is there. But that can be nice for if you're just looking up, how do I do a kind of what I would think of as like a bread and butter data exploration type task. I just need to remember the command for frequency table. How do I do that? Stat methods, Quick R, I think can really walk through those commands in a way that can be really nice. Something like Stack Overflows can be more for troubleshooting and finding solutions to your problems. And just some sources I've used today. But so in the last couple minutes, just going to kind of quickly, and I'll admit I'm certainly going to be glossing over this a little bit, but just to sort of jump back so you're aware of different tests that are available. But again, that site, statmethods.net, that Quick R resource can be really good since there's no real need to remember all of these things. So when we talked about heat maps, you may recall we ran a table where we were making a chart of the correlations of gene expression. And so if we're working with just trying to pull out the correlation coefficient, a command in that case we used was COR. And I remember at the time there was a question, what is COR? COR was basically pulling out the Pearson's R, I think is the default. We could also use that and set it from Pearson to Spearman. Spearman's going to be the test for non-parametric data, so not normally distributed data. And that produces the row value. But basically, it's telling you how much does the data correlate. This core.test can be nice because, again, it does give us a little bit more information, like the confidence interval, which perhaps for these massive gene expression data sets, not going to be as helpful, but for more kind of small data standard sort of comparisons might be something or would definitely be something that would be good to be aware of. And for small data sets, we don't have any. So if you have less than, my understanding is if you have less than 5 observations for a cell, the Fisher's exact test might be an alternate, would be a good alternate for the Pearson's correlation, since that's not really designed, or it's not very robust for small sample sizes. With the Spearman option, it does give us this warning. There is a way you can turn off the exact p-value, but you do get this warning. And in general, warnings you should pay attention to. But if you get a warning in R, it is good just to remember that it is still going to be running. It's not going to stop effectively. An error, it is going to stop running the command. When R hits an error, it will stop and you'll have to Google it, or more realistically, you'll have to figure out where your typo was, and go on from there. Things like if you're doing analysis of variance, the ANOVA, it is a little bit different than in other tools. So in terms of statistical tools, my other exposure to doing ANOVA would be using SPSS. Yours may be different. And it's good just to be aware that it's kind of a two-step process in R as compared to, say, SPSS, where you kind of just are providing this ANOVA command with your dependent and independent variables. So here you're going to first run AOV, and then you can either run summary or ANOVA. As you can see, they pretty much produce the same output. So you've got your p-values, your f-statistic, going over your sum of squares and your degrees of freedom. It looks like the ANOVA option is a little bit more precise in terms of the numbers it's giving us. So that may or may not matter for your research. But on the back end, basically this AOV command is running a linear regression. But for these where we're comparing multiple groups, as opposed to say the t-test where we're just comparing two groups. So these have groups within them. And we can see if it's saying if it's statistically significant or not. It's saying that in some of those, in at least one of those levels of comparison, that there is a statistically significant difference. If we wanted to write out to do a full linear regression, we could run this LM command. So what we could do is we could do the dependent variable, or basically what is it that we're trying to predict for, and then this tilde, which on my keyboard is above the accent mark, again, next to the 1. If you hold shift, you'll get the tilde. Good just to be aware of where that is, since that character does come up a good amount in typing in R. And then we can put in our independent variables. If we had an interaction variable, it would be done with a colon. So if we thought that A1C and diabetes were interacting, we could do plus A1C colon DX underscore diabetes. And then the last thing is just the data frame to pull these from. And then we can, again, similar to as we saw with the ANOVA, we can run a summary to see information. So we could look at the residuals, so we could chart those. The assumption is going to be that the residuals are normally distributed. In this case, they're not. Also, in this case, while I'm using this to demonstrate LM, it's important to note that this is a bad model because A1C and glucose, while measuring different things technically, they're very related. To be honest, I'm probably going to mix up the definition. My memory is that the A1C is testing blood sugar over a continuous period of time or a longer period of time, and it's doing that by testing the amount of sugar that's on the surface of blood cells. Blood glucose is exactly at that moment reading. So they're very related measures. So they're not actually, you're kind of testing the same thing. So it's not a good model on multiple levels. But on top of that, we can see that it's giving us our residuals, and then it's giving our coefficients, the estimate of the coefficient. So basically, how much does an increase in the one correspond or correlate to an increase in the other, giving us the error, the t-value, and the significance, and then going down, just the residual standard error with the degrees of freedom and the f-statistics for our linear model. So again, mostly just mentioning this so you're aware of how you can read that in. And again, it's going to be LM for linear model, and then the dependent variable, so what we're interested in seeing, what's predicted by the independent over here with a comma, and the data frame, or the data, data frame. One thing I'll note, something I have not talked about, some researchers really like, I am not particularly enamored with, is a command called attach. And it's written, I'll do it down here, move this up. The reason I don't really love this command is, so attach, sorry, let me tell you what it is and then tell you what it does. So there's a command called attach. Basically what that does is currently we have this global environment, and we're in the global environment, and we can reference any of these data objects. So you can see I've not closed and cleaned out my R in a little bit, and so I should probably, for the sake of my sanity and my computer, do that. But if we want to say get the mean cholesterol, we have to say NYC $cholesterol. There's a command called attach. So if I do it here, NYC, now we are in the NYC environment. If we said mean cholesterol total without having to say NYC, it will give that. We already removed the NAs, that's why it works directly. So if you're definitely going to be working exclusively in one data frame, it may save you some time in terms of typing to do that. The thing I don't really like about it, and others that when I've read about it don't love about it, is you do have to really remember that you have attached NYC. There's nothing outward to let us know that we are no longer in the global environment, at least that I'm aware of. And so when we want to stop being in NYC, we do have to say detach. And now we're back in. So if I was to run the same mean, it's going to say, what is that? Because it doesn't know to reference that without referencing NYC. So perhaps you'll really like attach. Remembering to detach isn't going to be an issue. For me, I don't love it for that reason, that it's easy to forget kind of where I am. And so that's sort of why I haven't mentioned it. It did just occur to me. It might be something you might want to work with and you may see done going forward. So good just to be aware. Attach means leave the global environment, which is where all of our data objects live, and go into the NYC environment where just these columns of NYC live. There's also the ability to run power assessments in R. There's a nice command or a library, excuse me, called power, PWR. And you can run both tests for if you have a, what's the word, a level of difference that you're interested in between your samples. You can find, for example, either what population would be necessary to get, a set level of power, or if you're just saying, I've done my test on X amount of sample with this significance level and finding this level of difference between the two groups, what is the, either what's the population or what is the power of my test. So this can be really good for the sake of being transparent when you're reporting results. Especially, I mean, within the realm of sort of reproducibility issues, underpowered studies are definitely a major issue in the scientific arena. And so providing that information for other researchers to know how reliable are your findings when you write them up can be a very useful thing to provide and a very transparent and clear thing to provide. And so it can just be good to be aware that you don't have to go to an additional tool. You can run from this power command an additional power test, and both going from either the levels, population levels you have, or from the level of power you want, what populations you'd need. So there's a few additional sort of on your own that you can work on. We're a little bit early, but not so terribly early today. So I do want to thank you all for joining us these past, I guess it's been 6 or 7 sessions. It's been a pleasure to teach all of you, and even though we haven't really gotten to know one another, of course, because of the format, it's been a great experience for me, and I hope you've all learned something. At the very least, feel the confidence that as you're exploring data, that you know where you might turn to find information about what functions mean, and that you feel prepared to go into the RNA-seq portion, the sequence analysis portion of this class. Definitely also want to make a plug for library resources. So I'm from the library. Definitely come over to hsl.med.nyu.edu. Let's see. So under the global environment tab, we can know which environment we are if we attach. Is it possible to fit the data to a theoretical model that is not linear? So there are, yes, it is possible to do more than linear modeling. I'm going to sort of leave off and leave questions of modeling to others, though. That will have to be something that you kind of explore on your own as somebody, somebody that you can definitely hopefully move on and explore. So yeah, I only talked about the one type, but you can do other types of modeling.
Fred, you should also mention the summer course.
Oh, yes. I mean, I will say, so I'm teaching a summer class that's going to be on R for analysis. I will say a lot of it is going to cover similar ground, though it will be a bit more problem-oriented. So we're going to encourage students to find a data set of their own interest or own choosing, and then kind of explore, use some of the things we've talked about, and kind of use some of these exploratory data analysis methods to find, find something of interest that they can then report on, and then using R again to create a presentation that they might want to present to others. So it'll be much more of a kind of problem-based learning. We will discuss similar skills within R, but especially if you've enjoyed what you've learned and you want to recommend to others who also, might benefit from learning R in the context of finding a data set and exploring that, definitely inform them about that. And yes, so we'll be teaching again in, I guess at this point, a few months. So again, I want to thank you for your time. And I think I'm going to go ahead and hit stop record, but